Okay, now moving into a couple problems here where we're going to use this concept Q to figure out what's going to happen in our system, which way we're going to shift as this system moves towards reaching equilibrium. So if we look at the first problem here, we're given a temperature and we're told the equilibrium constant for this reaction provided is 50.5. We want to predict in which direction the reaction will proceed to reach equilibrium given quantities of moles of each of the components and then the volume of the solution. So this is an important thing to keep in mind. Equilibrium based on concentration, we need to factor in the volume of the solution. If that's not 1 mole of solution, then how many liters of solution, but that's not 1 liter of solution, how many liters of solution will be important in doing the calculation. So let's start with figuring out these concentrations. So the concentration of hydrogen here is given as 1 times 10 to the minus 2 moles. So that would be 0.01 moles of hydrogen. But in a 2-liter solution means we'd have to divide by 2 there. So the concentration of hydrogen would end up being 0.005 molar. Right now, everything is 2 sig figs or 3 sig figs for the volume, but I'm going to leave that second zero or that last zero off here just for brevity's sake. The concentration of I2 in this case, we're told there's 3 times 10 to the minus 2, so 0.03 moles of I2, but that's in 2 liters, so that would be 0.015 molar. And the concentration of our product, hydrogen iodide, there's 2 times 10 to the minus 2 moles, or 0.02 moles in a 2-liter solution. That would be 0.01 moles of HI in solution. Now, we know all these concentrations, right? But we don't know if this system is at equilibrium. So this is exactly the type of circumstance where we would want to calculate Q. Now Q, same setup for the Q expression as for the K expression, or equilibrium constant expression. It's going to be the products, which in this case is HI, squared because of the 2 in the stoichiometry of the reaction, divided by the reactants, so H2 and I2. And since we have those concentrations, we just figured those out, we can plug those in. So this would be 0.01 on top squared, hydrogen 0.005, and iodine 0.015. And if we punch all that into our calculator, so 0.01 times 0.01 divided by 0.005 divided by 0.015, right? We get 1.3, and it's repeating, but we really have 2 sig figs here, so 1.3 is just fine for Q. So if Q equals 1.3, we want to compare that to the equilibrium constant for this reaction. That was given in the problem, K equals 50.5. So now to kind of figure out what this tells us, we want to look back at the expression here that defines either Q or K. Right now, we're at 1.3. By the time we get to equilibrium, this expression is going to equal 50.5. And that tells us that the quantity on top of the fraction is going to have to increase. The quantity on the bottom of the fraction is going to decrease. Now, in terms of the reaction, that would mean the reaction is going to shift forward. So a lot of the material that's currently in the form of hydrogen and iodide is going to have to end up in the form of hydrogen iodide. So the fact that Q is less than K here means this reaction shifts toward the products as it approaches equilibrium. Or you could also say that as forward. It shifts in the forward direction. Okay, that's the kind of analysis that we'll do with Q. So whenever we have a system and we don't know if it's at equilibrium, that is how we want to approach that particular problem. Okay, second example here. Now this one has the equilibrium constant based on pressure we talked about before. So if that was a little unclear, we maybe kind of show the difference here. So given temperature, we're given the equilibrium constant for the reaction, right, 0.338. We want to calculate QP here, Q based on pressures, and predict direction. Right, and down at the bottom, we're given the partial pressure of each of the gases, SO3, SO2, and O2. So we don't need to do any additional calculations here to get in the right form, so let's just start with the Q expression. Again, it's going to be products over reactants. So in this case, SO2 is one of my products, so I want the partial pressure of SO2, but that's going to be squared again because of the stoichiometry of the reaction. I want to multiply that by the partial pressure of O2, right? No square there because just 1 mole of O2 in the reaction. My reactant is SO3, so partial pressure of SO3 will go on the bottom here or in the denominator, and I'll need to square that. So I've got those partial pressures already, so I can plug them in. So 0.41 atmospheres for SO2, that's going to be squared. O2 is 2.5 atmospheres, and then SO3 is 0.16 atmospheres, and that's going to be squared. And I just need to punch all of this in. So 0.41 times 0.41 times 2.5 divided by 0.16 divided by 0.16. And again, this is really two significant figures here based on our partial pressures. So Q would be 16 here when I round out that answer. And again, what we're doing here really is thinking about how this value compares to K. So we have Q here equal to 16. The equilibrium constant we were given in the problem is 0.338. So this is sort of the opposite situation as we saw in the first problem. Instead of Q being less than K, now Q is greater than K. Right? And what that tells us is right now, right, this is too high. The value we get when we plug in these pressures is too high. The way to lower this value is to lower the pressures that are on top of this fraction, increase the pressures that are on the bottom of this fraction. Now that would correspond to a shift from the products to the reactants. So some of the oxygen molecules and SO2 molecules are going to need to combine to form more SO3 molecules. So since Q is greater than K, this would shift toward the reactants as we move toward equilibrium.